Hi there. I'm going to describe the proof of the Monty Hall problem. This interesting problem. This has been proven maybe somewhere else, but I don't think that they have made it the way I did, or even I didn't see it. I don't know. Anyway, I'm assuming already you know the Monty Hall problem. Like you have like three lockers or three rooms, whatever. Each one has a door, and you are a player. And there is a treasure inside one of them, and there is Mr. Monty here, like, and he will guide you through the process, through the game. And let us state something. This kind of proof is actually made for people who are like me, who are not very aware of probabilities much, but like to see things on the paper. Okay, perhaps it can be proven intuitively somehow. Yes, but if you want something on the paper, so I hope this can really help. Let us state the problem. This is state some events actually. I think there are three events, three main events. There is the event that you choose. For example, you as a player, you choose A. This is the first choice, not the second after Monty opens the one of the doors. Again, you have to already be familiar with the problem. I won't describe it here. It's described in Wikipedia and some YouTube videos, etc. So this is the probability of the first choice. The probability that you choose A. Let me just write it down here. Player, like you, chooses the door A. CHB, player chooses B, and CHC, player chooses C. Okay, let me focus the camera. So this is like the first event or incident. Now, consequently, Mr. Monty can open either A, or can open B, or can open C. Of course, if you choose A, he won't open A. This is part of the game. But let me just state them. Probability OA, I'm sorry, not yet probability, we're just stating events. Monty, or the Monty, yeah, opens A. Monty opens B, Monty opens C. And consequently, again, there's the third event, that is your next choice. Actually, we are not interested in, I'm not gonna state like the next choice. No. In fact, I'll state where the car is. The car is at A. This event is the car is actually at A. Car is at A. Or I'm saying car, it can be treasure or anything. CB, car is at B, and CC, the car is at C. So, what now? Actually, let me just state some probabilities now that will be useful in the proof. And then I will state what we need to prove, okay, and we will prove it. The probability what is the probability that you firstly chose A? When you come into the three doors, the probability that you choose A is equal to the probability to choose B is equal to the probability to choose C, so it's 1/3. Everything is equiparable to you. And what is the probability that you choose B? Again, it's 1/3, and probability that you choose C is 1/3. We're not going to use them all anyway. Okay, so what is now the probability that the car is at A? What is the probability? Actually, the car was placed maybe long behind the game started, long before the game started. So the probability that the car is at A is really equiparable. I mean, the game organizers actually put the car in A or in B or in C, so it's gonna be again 1/3. And it has nothing to do with your choice, nor with what Monty will open. So the probability of that the car is at B is 1/3. This has nothing to do. The car is at A has nothing to do with what you know or what Monty knows. What Monty knows is very interesting, by the way, because this is would determine which door he would open. Again, based on what you already chose. Okay, like we have like 3 events here. The probability that the car is at C is again 1/3. So let us now state some probabilities that are actually part of the game. Right now there is nothing. Let us start with the game. What is the probability that Monty opens like the B door such that this is a conditional probability such that the car is at A and you chose A. Now, which door Monty opens actually is related to what he knows. He already knows that the car is at A. Okay, but when I state such that, this has nothing to do with what he knows. What he knows is inside this. Okay, CA, the car is actually at A. Like you have firstly chosen the car. The car is at A, and you've chosen A. So you firstly chosen A, and the car was at A. So Monty actually, what would he do? He can open any of these 2. This is the game. It doesn't matter. So it's like now 1/2. It's now 1/2. And what is the probability that Monty opens B? C actually. Let's again continue the idea. Again, the same condition, and you've chosen A. It is 1/2. And this half actually came from this one, and this one came from this one. Like they are interworking together. Now, again, let us state something, continue the game. What is the probability that Monty opens B such that Monty now would open B such that you've chosen B? This would be Monty would never opens it. Okay, it is 0, and I don't think that we're gonna use this, but I don't know. It's mentioned, not a big deal. Okay, what is the probability that Monty? This is really not very evident. I mean, this is part of the game, but we may not use it. What is the probability that Monty opens C such that the car was at A and you've chosen B? Now Monty has no choice actually but to open C. The car is at A, you've chosen B. Okay, you've chosen B, the car is at A. Now he has to open C. He has no way but to open C, so it's 1. Again, what is the probability that Monty opens B such that the same conditions? You've chosen B. This is part of the game. Never like this one. What is the probability that he opens A such that the car is at A? And actually, this is what has to be mentioned probably. What is the probability that he opens A such that the car is at A and CHB? That would be 0. The car is at A. How can he opens A? He won't do it. This is evident. We may not use it anyway. So this is like what we're gonna use in the proof. But what do we need to prove? What we need to prove is this, is that the probability that the car, for example, I'm taking one case, and I'm taking the case that that Monty opens, for example, C, and you've chosen A. The player chooses A. So the player chooses A, Monty opens C, and let us and this is the probability that the car is at A. Let us think about it a little. What is the probability that the car is here, such that Monty opens what is the probability that the car is here, such that Monty opens this, and you've chosen this? Okay, and what is, sorry, I'm thinking with you, probability that I'm writing down from another piece of paper that you don't see right now. Actually, the Monty Hall problem, what people fall into is that they think that these two are equal. Intuitively and wrongly, we think that they are equal, but they're not. Probability that the car, that you've chosen A, Monty opens C. Okay. You've chosen A, Monty opens C. So people might think that really it doesn't matter. The probability should never change. Okay? The probability should never change. Like it must be 1/3 again. Even if he opens C, the probability has to remain the same. But this is not true, and we will prove it. So this is the first idea. The car, what's the probability that the car is here? So what's the probability that the car is here while you've chosen A, and because since Monty opens this C, now you have two choices. You have to either remain at your positional option or change your opinion and chooses B. So people might think that they are still the same, like conserving the old probabilities, 1/3, 1/3 maybe, or 1/2, 1/2, or the new probabilities would be like 1/2, 1/2. People might think so. So actually, this is what people fall into. But the problem actually goes, in reality, it is like this, and we will have to prove it. The probability that it is always advisable that you change your opinion, that you chooses B. After that, Monty opens C. It's always advisable that you change your option. Likewise, what is the probability that say, for example, Monty opens B and you've chosen A, so now you have like two choices, either A or C. So you have to choose that. You have to prove now that the probability at C is like bigger than the probability at A, such that the same conditions, like if chooses A and Monty opens B. Anyway, we will stick to this. If we were able to prove this, then it will be sufficient. I hope you really agree with me right now. So how are we gonna prove this? We're gonna use Bayes' theorem. I'm just gonna call this P1. Okay, so P1 equals to probability that CA and OC, this is Bayes' theorem. Bayes' theorem. Actually, and all this, and CHA. But this is not really interesting, anyway. Over over the probability of what? Of this thing. Which can be put slightly in another way. Probability that CA enter OC intersection CHA over the denominator. Now here I will enter CHA, enter I'm gonna introduce like intersection thing, something, plus probability, this same thing here, intersection, its complement. Actually, Bayes' theorem suggests that we use this, and we're still here, CA, and not in CA. Something here now needs to, what does that mean, not in CA? Okay, actually this directly means something. Again, let's state the problem. We've chosen A and the car is at C. Now actually, what does that mean, that not at A? It has to mean the car is at B. You may prove it anyway. This is something to prove, but it's like almost evident, because if we were to put like intersection C and the plus or like plus OC CHA CC, this cannot happen. If you open C, you cannot choose the car at C. So that's it. This is evident. So let us now, we have to find this value and we have to find that value. The probability that CA intersection OC intersection CHA. Now what is that probability? Now we're gonna use these things. The probability, again, the conditional probabilities, these things are not independent. So we have a very great tendency to use something like that. Now, probability of OC such that CA enter CHA times the probability of this thing, which is the car is at A and you've chosen A. Now these two events are independent. I mean, you feel this strongly, because what is the probability the car is at A? This is really independent of what you've chosen. The car was already long before, and when you've chosen it, they're really not related to each other, and they're independent. So this thing, we're gonna put its value here times, since these two are independent, so it is the probability of CA times the probability of CHA. What is the probability of OCCA? This is the same as here. It is 1/2 times 1/3 times 1/3. That would be like 1/18. Okay. Now, as for the probability of this one, let me just bring another piece of paper. Now the probability of OC intersection CHA I'm taking this term aside, intersection CB, and we have a big tendency to use something like this, or this actually, OCCA. It's not mentioned here, but it's not that difficult. We're gonna do it. We actually, what we know of the problem is this, is like OC such that you've chosen A and the car was at B. I'm sorry, times the probability of this thing. This is what we do when this event and this event are not independent. Intersection CB. So again, the statement of the problem, we have the probability that you've chosen A and the car is at B. You've chosen A, the car is at B. Since you've chosen A, Monty would open, for you, Monty would open B or C, but since the car is at B, so Monty has no choice but to open C, okay? Probably chosen A, the car is at B. Monty already knows it, so he would open C. So the probability that he would open C is 1. Times, again, these two are independent, so it's 1/3 times 1/3. All in all, this is, I'm sorry, let me focus the camera. This is 1/9. Now, this is 1/9, this is 1/18, this is 1/18. So this P1, okay, this P1 would be, what would it be? 1/18 over 1/18 plus 1/9, which it is 1/3. That's interesting. 1/3. Actually, if you do now this thing, I'm sorry, yes, we have to prove this thing. Say, name it P2. Do it the same way. P2 would be 2/3. And now you're very happy with your proof. This is 2/3 and this is 1/3. So you really have to, and you have to change your opinion whenever Monty opens something. Go ahead, change your opinion. The car was at C. You've chosen A. They are not the same. The car is at C. You've chosen A. So go ahead and change your opinion. Go to B. Even if you don't know where the car is. Okay, good luck.